Hello, everybody, and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. And this is lecture number 66, which is electrothermal small signal model of nanosheet FETs with ZTC or zero temperature coefficient based parameter extraction methods. We will start from where we had left in the previous discussion, and this shows absolute early voltage variation with channel length. And as is expected, as the channel length actually starts to reduce, the early voltage also tends to go down and down. If you see, it actually goes down as the absolute early voltage goes to go down as the channel length starts to reduce drastically. Now, the authors have used a VDS of 0.7 volts. VGT is basically the overdrive voltage, which is basically VGS minus VTH, right? Which is the gate to source voltage minus the threshold voltage, and temperature is 25 degrees centigrade. Now, if you look at the gate stack, so these are for two types of gate stacks, and this is for M star and this is for gate N star, right? For a lower channel length, the difference between the two gate stacks don't have too much amount of meaning. They are almost the same in terms of early voltage, but the early voltage becomes much larger at higher channel lengths. And this is primarily because of the fact that at lower channel lengths, because of lambda or channel length modulation phenomena, you do have these variations taking place here, right? And smaller nanosheet separation also enhances the gate control and therefore improves performance. This is the intrinsic voltage gain, which is the V by V voltage gain in dB with respect to channel length. And as you can see, that gain increases, the absolute voltage gain increases with channel length. And this is quite sort of detrimental in terms of design parameters when you are discussing the channel length. At lower channel length, you will see that your gains are relatively much smaller, right? And in dB terms, it is about 8 for the gate stack N star. The difference is approximately more than 10 dB. Around 10 dB is the difference, which is quite a lot as you move from 200 to around 10 or 10 nanometer channel length. Please understand the channel length L is in log scale, right? So you can see they are quite separated in a sense. And N star gives you relatively a larger voltage gain as compared to your M stack gate stack, right? Which means that stronger electrostatic control will give you obviously a larger gain, right? And that is expected also when you are talking of intrinsic voltage gain with respect to channel length. Now, we will do the same thing, intrinsic voltage gain, which is AV versus temperature we have found out. So, if you see the left hand side, this is for stack M star and this for N star. And in both the cases, for a larger channel length, your gain is obviously larger. But what we have seen interestingly is that somewhere around T equals to 300 or 100 Kelvin in the first case, in M star case, the gain is also maximum. Whereas in the second case, when you are using gate stack of N star, it is typically for lower channel length, the gain is maximum at 25 degrees centigrade, right? So at room temperature, your gain is maximum, and but as you increase the temperature at lower channel lengths of 28 nanometer, the gain starts to reduce after that. And there's a good amount of thermal stability of the nanosheets are available here, right? And the overdrive is again taken to be approximately equals to 200 millivolts in this case, and the channel length is varying from 28, not varying, they're kept at 28 and 200 nanometer. For this case, it can be seen that if you compare this even with FinFETs and SOI technology, the NSFET technology performs better than FinFETs as compared to any SOI technology. And the gain is typically in terms of 46 dB, which you get, maximum gain which you get is around 46 to 47 dB for VDS equals to 0.7 volts and overdrive of 200 millivolts. This is basically the unit gain frequency with respect to inversion coefficient IC. The unit gain frequency is defined as GM sat, which is the saturated transconductance, divided by 2 pi CGG. So, FT is defined as maximum GM sat divided by 2 pi CGG. CGG is basically the gate stack capacitance which you see, and the total capacitance. And if you plot FT with respect to IC, where CGG is basically the total capacitance there, and basically the FT with IC is the normalized inversion coefficient, and this is basically drain current normalized to the threshold voltage, right? So what we do is that we change the drain current, check the threshold voltage, we divide the two, and we plot that as an IC, and it varies from 0.01 to approximately 100. So log scale is there already in the x-axis, and it is meant for two stacks, the upper and lower one, A and B. Within A and B, we have the black one is your N star, and your red one is basically your M star, which is available to us. Now, in the second case, we are again using VDS of 7.7 volts and overdrive of 200 millivolts. So we will see that these are weak inversion regions on the left hand side, and as you move towards on the higher side, you get a strong inversion region coming up, right? Higher channel length, if you look from the point of view of channel length, higher channel length will actually give you the better FT, right? So higher channel length gives you a reduced value of FT, and lower channel length gives you a much better. So if you look at this black curve is for lower channel length, and this blue one is for this one. So higher one, the black one, the lower channel length gives you a better FT as compared to your case, be it N stack or M stack in that case, right? So the upper one is A is for N star, and the B one is for M star, right? And that's the reason the unit gain frequency is relatively small in this case. Now, if you trade off between the FT and the efficiency, then on the left hand side, on the y axis of the graph here, we plot GM by AD into FT, and on the y axis we plot IC. Then also the same observation is occurring, that somewhere around 10, IC value of 10, you see the maximum value of the GM upon IG into FT is coming into picture, right? The optimal operating point corresponds to the peak of the curve, where FT and the efficiency balance with each other. As you move further ahead of it, the value of FT goes on falling down, and therefore you see a drop in the value. And for both the cases, IC is equals to 10 has been taken into account this thing. And by doing this analysis, we will be able to ascertain the bias points where I get the maximum speed and efficiency sort of match I can do using a trade-off between FT and efficiency in a sense, right? And that is quite an interesting phenomena which people tend to do over a period of time. Now, if you look at the optimal operation point, that is IC versus channel length at different temperatures, then on the y-axis it is IC, and on the x-axis is channel length. And for N star, the IC is around L equals to 200 is to 70 nanometer, shifting with temperature. And for M stack, the IC is in MI for short channel length, but shifts to strong inversion for longer channel. For strong inversion, it shifts to the longer channel length. With increasing temperature, a slight reduction in the IC value is observed, while longer channel lengths show an improvement in the robustness of the optimal point. Let me now, so this takes care of our understanding of the major IDVD and IDVG characteristics of NSFET. For all practical purposes, we have understood those basic issues now. We will now come to deep dive into the reliability issues and the thermal issues, as well as parameter comparison. So our next subtopic is basically self-heating effect. We will look into the thermal network parameter extraction and S parameter comparison. We will have a look into all these things. So what is the self-heating effect? Now, self-heating basically means that whenever you do have a large current flowing through the NSFET or nanosheet FET, because of carrier scattering, there's a Joule heating happening, right? This Joule heating, if you are not able to dissipate this heat properly across the network, the temperature will go on rising beyond a particular point, right? The temperature will go on rising, and as a result, you will get hotspots at various active areas of the device. This is referred to as self-heating. That self-heating means that the temperature within the device itself rise, and it's basically a cyclic process, because of which, as the temperature rises, the scattering becomes more larger, Joule heating becomes larger. When Joule heating becomes larger, it further makes the thermal effect go larger and larger near the active hotspots. In nanosheet FETs, since so you understand nanosheet FETs are aligned in this manner, right? And in nanosheet FETs, the heat dissipation path is very much restricted. You don't have anywhere the heat can get dissipated either into the sink or into the active area of the device. And this leads to the rise in the lattice temperature. The lattice temperature goes on rising, right? It's basically a cyclic process which happens, and this gives rise to rise in the lattice temperature. The local heating also modifies the lattice temperature distribution in the device. The local hotspots which you see, the local heating which you see at various points within the channel, from, for example, at this particular point in the channel, the temperature goes on rising to a larger extent. The elevated temperature influences carrier mobility, and therefore the thermal management of nanoscale devices is very, very important. As the temperature increases, as you can appreciate, more will be the scattering, and as a result, your mobility degradation will be much larger in this case. Now, if you look at figure A on the left hand side, we can see that in both the cases from cross sectional area, the heat is actually more concentrated towards the drain end of the device itself, right? Source side is relatively cooler. So, all the red colored device, more you go towards red, more heated up it is, and more you comes towards the blue side, less heated it is. Now, more heated is primarily because of the drain end you have velocity saturated phenomena, as well as the density of current is also larger, and therefore you will typically have a much larger sort of current, and therefore the heating effect is also larger in this case, whereas source side is relatively much cooler. Now, if you look at the flow chart for electrothermal coupled small signal modeling, we generally find out what we find the value of IDVG. If you look at the right hand side flow chart, we find the IDVG simulator with self-heating effect for multiple temperature. We extract the 0 TC point for saturated case. Then we go for small signal parameter extraction at with self-heating effect. We look into the Y parameter, Z parameter, and then we extract the equivalent thermal equivalent resistance and thermal equivalent capacitance. When we do that and we compare with the model parameters RTH, we do a curve fitting. When we do the curve fitting and we see that the ZTC model is fitting properly, we change the value of delta T at different gate biases, and then we finally find the value of the model parameters variation with respect to delta T. So, this is the general scheme of things which most of the researchers follow when you do an electrothermal coupled small signal modeling in this case, right? And we looked into bias dependent properties with self-heating effect and without self-heating effect, right? Now, in both the cases, when we try to find out with self-heating and without self-heating, we try to extract the value of the various parameters which are available in the device structure itself. Now, finally, the two equations which come out, these are the two equations. Looks complicated, but when you actually apply to it, it can be easily done, where we do the imaginary and the real part of the thermal coefficients, and where omega is the frequency of operation, R is the thermal equivalent circuitry, and C is the capacitor which you see. So, from these relations we will be able to extract. So, my final aim from all this discussion is that we will be able to extract the thermal resistance, and the capacitance can be easily extracted by the techniques which I have shown in this case. Once you have done that, we will just plug and place those thermal resistances and capacitance in the electrothermal coupled small signal circuit. So, if you see, the intrinsic part is this one, and the extrinsic part is basically this one which you see, and this is my source or bulk region, this is my drain region, this is my gate region. The gate region, you have LG and RG coming into picture. In the intrinsic part, you have gate to drain resistance, gate to drain capacitance at this particular point, and then you have within the intrinsic part, you have gate to source current as a form, which is other capacitance, junction capacitances, and CDS and substrate resistances, all are mentioned within the red sort of jacketed part, which is the intrinsic part. So, as I discussed with you, when you do de-embedding, you actually do the intrinsic part and you do the extrinsic part separately, right? Now, so basically the RC ladder network which finally comes up after all these discussion is on the right hand side, that the network is something like this, where you have parallel combinations of resistances and capacitance, and from there you can find the effective thermal Z value, right? Now, extrinsic parameters are removed. This is a standard method when we do methodology for a cold FET and hot FET. So, in a cold FET, using cold FET method, so what we do is that extrinsic parameters are all removed and you just look at the intrinsic parameter concentration, and therefore, since self-heating does not influence Y11 and Y12, you can extract the capacitance from there directly. Whereas these parameter RGD, CGD1 and CGD2 can be extracted using a frequency dependent formulation, right? Whereas R sub, CGD and CDS from zero bias Y parameter analysis can be taken care of, right? Now, the thermal impedance ZTH is represented by the distributed RC network, as you can see, and the modeling framework establishes that the small signal equivalent circuit for NSFET focusing on intrinsic parameter is being done in this case, right? Now, With this discussion, as I discussed with you, the ZTC point is defined as the gate to source voltage point at which the current remains nearly constant independent of the variation in the temperature variation. Now, why this is true? Because two opposing forces work at these places. What are the two opposing effects? One is the reducing threshold voltage, and another is the decreased carrier mobility due to the rising temperature and balancing each other. Now, typically, so decreased carrier mobility due to rising temperature balances each other, and therefore the temperature sensitivity to the variation in the value of drain current is barely minimized, right? In this case, Y22 is biased at gate to source voltage of at 0 TC. At 0 TC, keep the value of VGS exactly equal to that of 0 TC VGS, and from there you can extract the value. And from there we extract the cost function CVGS and the formula given here. So the cost function tells you an idea about how we are working. Now, this is the thermal network parameter extraction which is being mentioned here, and on the y-axis you have the IDS value, and on the x-axis you have VGS in the first graph. In the second case, the cost function is varied with respect to VGS, and as you can see, at 0 TC point your cost function becomes minimum, right? And therefore, as the temperature increases, as you can see for various values of temperature, ambient temperature, the curve shifts due to the combined effect of mobility reduction and threshold voltage reduction. At 0 TC point, as I discussed with you, the crossover takes place, and you do have the variation in the value of IDS with respect to VGS. If you look at the cost function, the minimum of this cost function occurs somewhere around 0.5 volts. And so we understand that if you operate somewhere around 0.5 volts, that will be the most optimal variation or optimal value of the output voltage performance wise. So what we are showing you here is basically the variation of ZTC with respect to width, sheet width. The WSCH is the sheet width, and this is the number of sheets which you see. If you go on increasing the sheet width, the 0 TC point, the gate voltage at which you get a 0 TC point starts to shift lower and lower, right? Though the variation is not so large, it is of the third order of magnitude, but nonetheless there is a variation which affects the 0 TC point. And this is one of the best way to extract the value of 0 TC point. Whereas on the right hand side, if you see, as the number of nanosheet increases, the 0 TC point increases also. So when you work with, let us say, 1 sheet, 2 sheet, 3 sheet and 4 sheet, with compared to 1 sheet, the 4 sheet gives you a variation of more than about 0.03 volt variation it gives you, right? So it gives you a substantially a large amount of variation in your 0 TC point, which means that so the cost function will remain not the same for all types of sheet voltages. They will vary with respect to number of sheets. This is the variation of conductance with the absolute value of CDD with frequency, and so this is the on the x-axis you have frequency in the log scale, on the y-axis you have GD, which is available to you, and for various values of VGS 0.4, 0.5 and 0.6 approximately, and we are using a VDS of 0.8 volt, which means we are in saturation region, and gate voltage of 0.5 volts. Why 0.5? Because if you remember, our previous discussion was that the cost function is the best at 0.5 volts, and that's the reason we have kept VGS value at approximately 0.5 volts. So we are varying it, and as you can see, interestingly, for 0.4 and 0.6, right? If you look at the cost function variation, when VGS equals to 0.5, it's almost straight. GD does not vary, and that's the whole idea of having the minimum cost function, that the variability is bare minimum. Whereas if you look at 0.4 and 0.6, the GD value suddenly rises and falls down respectively around 10 to the power minus 8 to a larger extent, and this is primarily because of gate resistance. As I discussed with you, the sign change indicates the impact of dynamic, the sign change in the terms of effective values of the GD. The sign change means this is going up and going down, right? The del GDS which you see is positive in case of green, negative in case of red colored. Now CDD at VGS equals to 0.62 is at VG remains larger than the 0 TC bias up to 30 gigahertz. So up to so if you look at the frequency characteristics, the best cost function gives you almost independent of the value of the capacitance. Now if you plot CDD versus frequency, then on the x-axis if you plot CDD versus frequency, you see a sign change happening somewhere at 10 to the power 7 and 10 to the power 9, right, for 0.4 and 0.62, whereas for blue color it is changing at 10 to the power 6, right. The valley at 0.40, the valley which you see, this occurs at a larger magnitude, right? And takes longer to reach to the positive value for the 0 TC case, because usually CDD at VGS zero point 0.4 is initially very small. So we will look into the extraction of imaginary value of the ZTH with respect to omega, and the results demonstrate that the ZTS based method with 0 TC based method provides a much better stability across frequencies, relatively at slow frequencies as compared to low frequency or intermediate frequency or high frequency. And this improvement stems from the fact that ZCT extraction is well defined bias points, where you say that your del IDS del TA is exactly equals to 0, right? And that's the reason it is much more stable expression which you get. Similarly, if you see the imaginary part of ZTH by omega with respect to frequency, and this is for the first order thermal network, this one is for the first order thermal network, this is for the second order, third order, fourth and fifth order thermal network, and this is the TCAD variation of the thermal network which you see here. The fourth and fifth order thermal network provides the best agreement, but since the fourth order network requires fewer computational resources, it is adopted as the optimal model for the study given by the authors, right? Fourth order optimal study variation comes into picture. This is the variation of RTH and CTH with thermal resistance, and what we can see is that the thermal resistance dominates for at VGS equals to 0.4 volts, and ZTC method shows an increased value of thermal resistance, whereas LFHF, which is the low frequency and high frequency method, gives more variation across VGS, and higher order resistances are much smaller in this case. And that you can see from the right hand side figure which you see here, that the thermal resistances are much smaller when you have the values are much smaller for fourth order networks, right? And that's the reason we prefer to have that as the most accurate value here. Similarly, if the extracted value of RTH and CTH are plotted on the top and bottom corner, and we can see that the RTH1 increases with higher VGS while the capacitance value decreases, and this behavior is linked to the increase in the thermal time constant. Why? Because your RTH and CTH value increases and tau increases, and therefore at higher VGS your thermal time constant increases, and that affects your transient analysis at the higher temperature. Now, if you look at the electrothermal model parameter extraction, the lines are basically the models here with self-heating effect. The extrinsic parameters are extracted under off state where VGS equals to 0.8 volts and VDS equals to 0 volts. And the comparison shows that the modeling error is approximately 2%, which is very small in terms of frequency versus real part and the imaginary part as well. The authors have also done TCAD versus TCAD simulated and model parameter variation, and this complete 0 TC model is based on the 4 graphs which is kept on the right hand side here, where the frequency versus real part of S and the imaginary part of S are plotted for various options available to us. And we see that both real and imaginary part of S show strong correlation between TCAD and the extracted model in this big frequency range. So the frequency range up to 50 gigahertz, we can see it is working fine, and the error is approximately equal to approximately equals to 2 parameter in that case. We finally end up using the model parameters versus frequency, and these are for GM. Tau m is the time constant, thermal time constant, and GDS drain conductance extracted using TCAD Y parameter model, and also using RTS CTH using the ZTC model for low frequency high frequency methods. And thermal angular frequencies are derived from RTHI and CTHI, and each marks a frequency over the model. And overall ZTC method enables much more precise electrothermal modeling and characterization of self-heating effect when using nanosheet FETs. So let me recapitulate what we have done till now. We have actually taken care of the basic idea of self-heating effect in this case. Using self-heating effect, we have also found out the various thermal effects, RTH, CTH values. We discussed from a couple of papers where 0 TC methodology of extracting these values were given, and this is by way one of the most accurate methods of extracting the thermal coefficients and thermal hotspots in a nanosheet. Why this study is important? This study is important because finally at the end of the day, when you do a high frequency modeling, the reliability of these devices comes under question. So if the heating effect goes beyond a particular point, there is a failure happening in the device, and that's the reason this structure or this idea is important. So with this, let me thank you all for your patient hearing. Goodbye and thank you.